See here, PV is equal 1 by 3 mv square RMS, and here what happens that at constant volume, so this V is a constant, so we can write down PV is equal to 1 by 3 m V square RMS. So this directly proportional to what we can write down, 1 by 3 m into KT here, because I am taking the VRMS is directly proportional to temperature PV. So at constant volume, so what happens is this, the V is also constant, we can write down, eliminate these terms, directly we can write down P is proportional to T here. This is the Charles law at constant volume. See here, why we are going for this kinetic theory of gases, it develops the molecular behavior and that can be mapped with how the ideal gas can behave. So hence, we are going for this kinetic theory of gases. By using our pressure exerted by the gas, we are deriving Boyle's law, Charles law, and also Avogadro's law also we can derive. See here, from that Avogadro's law, we can write down PV is equal 1 by 3. This is the total mass of the gas. We can write down number of molecules N1 and V1 V square RMS. See, another gas we are taking 1 by 3 N2 M2 V square RMS. So our Avogadro's assumptions, same pressure and volume here, at temperature, all the molecules, all the gas having same molecules. So PV are the same, even same temperature, V square RMS same. We can write down at same temperature, they maintain same thermal equilibrium. V of mv square RMS is equal of m1 and m2 here, V square RMS. So from this we can write down both will have same number of the molecules. So from the kinetic theory of gases, we derived the basic laws. One is Boyle's law, Charles law at constant pressure, and Charles law at constant volume, and Avogadro's law. See, so what we discussed from this pressure exerted, PV is equal 1 by 3 P here, V square RMS. Another law here, 1 P is equal 1 way of this V into V square RMS. See, from that Boyle's law and Charles law and Avogadro's law, we are taking the ideal gas equation, PV is equal N or T, N is the number of moles. See, from this, N is equal number of moles, this you can write down N by number of molecules by Avogadro's number. This is number of molecules by Avogadro's number. And we are taking this ideal gas constant R here. This can be what we can write down, Boltzmann constant K and Avogadro's number. If we are substituting these two values, what we can get this, PV is equal N by Na into K into Na into T here. See, from this we can write down NKT here. These two equations that explains that ideal gas equation. One is in terms of number of moles, this is ideal gas constant here, and temperature, absolute temperature. Here this N, this is about number of moles here, this is number of molecules, this is Boltzmann constant. K is nothing but Boltzmann constant. So from this, PV is equal 1 by 3 number of molecules is N, and M is the small mass here, M is the mass of the one molecule, V square RMS. If you are comparing these two equations, PV is equal to NKT here. This is N is number of molecules, here also this N is also number of molecules. If you comparing these two equations, there is left side P and V, pressure of the gas and volume of the gas here. This is number of molecules and this is also number of the molecules. If you are comparing these two results, we can write down 1 by 3 m V square RMS is equal to KT. So V square RMS is equal 3 KT by, this is small m, mass of one molecule. So V RMS is equal to under root of 3 KT by m. So from here, initially we derived VRMS is equal to 3 P, see here P is equal 1 by 3 rho V square RMS. So VRMS is equal 3 P by rho here. This is the expressions for VRMS. Simultaneously, we are taking this instead of NKT, we are taking PV is equal to nRT. We are getting VRMS is equal to under root of 3RT by m here. This is the molecular weight. So, if you compare that, don't confuse about this. This is about 3 kT by m here, this 3 RTM. This m is the mass of one gas molecule. This is the molecular weight of this gas. So, another speeds of the molecules of the gas, speeds of molecules. One is VRMS and one more is average speed and one more is most probable speed. Here VRMS is equal to 3 kT by m here. If you are taking this average, this will be under root of 3 kT by m. So, this can be I am writing 3 RT in terms of molecular weight. Here average speed, this will be 8 kT by pi m. So, this can be 8 RT by pi mw. Here most probable speed, this is the more number of the molecules which will possess the speed that we are calling as most probable speed. This will be 2 kT by m here, this can be 2 RT by mw here. Suppose if they are giving mass of one molecule and Boltzmann constant, you substitute these formulas. If they are giving that molecular weight, you substitute these formulas. So, here simply what we are doing is the K by m is replaced by R by mw. So, this is mass of one molecule, this is the Boltzmann constant, this is about that ideal gas constant. See, this is about the molecular weight. So, in examinations, generally they focus on about these values and this relation between this pressure and density of this one. See here, suppose if we are given as one question like this, suppose calculate VRMS speed of oxygen at room temperature. Here oxygen single molecule mass is not given, but we know that molecular weight of the molecular weight of this oxygen. Better we are going with this formula by substituting, and VRMS is equal 3 RT by mw here. You substitute R value, room temperature is given, corresponding that molecular weight. This way we have to find out the VRMS speed of the oxygen. Suppose another question, see here, suppose they are asking that calculate the ratio of the mean speeds hydrogen and suppose nitrogen at the mixture of sample. Then you have to substitute that mean speed, you have to find out the average. Mean or average, both are the same. This is a way to substitute these formulas. The next one in the kinetic theory of gases, we are starting with degrees of freedom. What do you mean by degrees of freedom here? Suppose if it is a gas molecule, it will have so many components, like it will have some translational motion and it will have some rotational motion and also vibrational motion. See, this degrees of freedom, it explains how amount of this number of independent terms, including translation motion, rotational motion, vibrational motion, that is explained by these degrees of freedom. Here, if you observe this translational motion, how we are taking this degrees of motion, translational motion here, let we are taking this coordinate axis like x and y and z. It may move along the x axis, along the y axis and along the z axis. The energy terms corresponding to these velocities, we know this kinetic energies. One is along this x axis of mv square x and of mv square y and of mv square z. So, in the translational motion, we can explain this degrees of freedom as one is of mv square x, of mv square y, of mv square z. So, number of terms independent terms is in translational motion is 3, whereas rotational motion same energy terms. Here we are having translational kinetic energy. In the rotational motion, we are having that rotational kinetic energies. They are in terms of Ix omega square x, of Iy omega square, and of Iz omega square. So here we have that number of independent terms is 3 here. In the similarly, another type of the motion that is called vibrational motion. So one is corresponding to potential energy, one is corresponding to kinetic energy. This corresponding to this one of k r square. Suppose there are the two molecules, it's like connected by the spring. The separation between the molecules are here. This separation gives. This is about that how they are related with this one or two molecules. And again, this kinetic energy terms we can relate it as of mu v square. This is about reduced mass or effective mass of two molecules. So here the translational motion and rotational motion of these degrees of freedom, they are consisting of the gas at room temperature, whereas vibrational motion at higher temperature. Suppose in our general calculations, if they are maintaining the room temperature, you can easily neglect this vibrational motion. So here number of independent terms is 2, but this vibrational motion, the degrees of freedom, can be considered at higher temperature. At the room temperature, you can consider as translational motion and rotational motion. See here, maximum number of independent terms in the translational motion is 3, rotational motion is 3, and vibrational terms is 2. Now we can apply how these degrees of freedom can be getting by this monoatomic, diatomic, and triatomic. Suppose if it is a monoatomic gas, so only one gas, one molecule, it will move along the x-axis, maybe along the y-axis, and along the z-axis. So this Vx, Vy, Vz are independent with each other. So definitely we can take this for monoatomic gases, the translational degrees of freedom, number of degrees of freedom is 3. But our assumption in the kinetic theory of gases, the size of the molecule is very, very less. If you compare to the rotational one, the rotational degrees of freedom can be neglected. So at room temperature only we are considering this translational as well as rotational. Therefore, for monoatomic gas, number of degrees of freedom is 3 here. Consider diatomic. It's like possess like a dumbbell shape. Here for considering this only translational first, it may move along the x-axis, it may move along the y-axis, it may move along the z-axis. So translational factors 3 here. If you come to the rotational motion here, let this is the x-axis, this is the y-axis and z-axis. Consider this diatomic along one axis like z-axis. According to that, moment of inertia with respect to z-axis will be 0. Only that energy will exist along that x-axis and y-axis. Therefore, the rotational motion, rotational degrees of freedom is 2. So these are considering the diatomic gas at the room temperature is total number of degrees of freedom for diatomic gas is 5. If we are considering at higher temperature, so then translational 3, rotational 2, and one more degrees of freedom, that is vibrational, that is also 2. So total 3 plus 2 plus 2, this can be 7. So example for the monoatomic gas, you know this hydrogen, helium here, monoatomic gas, helium, argon, all the inert gases. Here this diatomic oxygen, hydrogen, these the things. Next, monoatomic, diatomic is over. Next one, triatomic.